All right, so it's a pleasure to have Alex here. Alex did his PhD in ETH Zurich, and then spent a couple of years in Toronto working with Raquel. He's done all sorts of wonderful work on computer vision and machine learning, particularly earlier on with structured models and so on. And now he's faculty for the last couple of years at University of Urbana-Champaign, UIUC. So it'd be great to hear what you've been up to. Yeah.
Thanks so much, Leonid, for this nice intro. Very happy to be here. I was actually here once in 2012 or something like this, just visiting the city, though. And I've been here on the campus. All right, now that being said, let me tell you a little bit about what myself and a bunch of students at UIUC, who really deserve all the credit of this work, are up to. And I usually call them the magicians because they're the ones that make all this work. So they're really the ones that deserve the credit. Now, if you look into the computer vision and machine learning literature, particularly maybe slightly more the applied side, you might gain the impression of, a lot of models actually tend to work quite well, right? If you look at tasks like image classification, object detection, semantic segmentation, or human pose estimation, we do have quite decent results. So, this begs the question, are we pretty much done? And I'm guessing you all wouldn't be here if you were done. What at least myself and a bunch of students are really after is the quest to personalize life. And what I really don't want to use is the way of automate life. I really like the word personalize much more. And what I think about is missing in order to get there is models that actually anticipate as opposed to analyze, which is models that are, or the models which we have right now are doing very well in analyzing, right? If you're giving them an image, they can predict where are the objects and what is happening in the image. But what many of those models can't do is anticipate what is going to happen 5 seconds down the road, 10 seconds down the road. And these are questions which I think are really, really important going forward if you look at tasks like autonomous driving. Right? We all, when we sit in a car and drive along a street, see two kids hassling each other, presumably chasing a ball without us actually seeing the ball. We know there might be one of two possible outcomes, right? Either the kids step aside and yield to oncoming traffic, or the kids run into the middle of the road without actually checking what's happening. Right? And as humans, we are very cautious in these situations. But I would argue that many of the models that we have so far are not able to actually perform these types of tasks and these types of reasonings. And in order to get there, I think we need to combine two visions that have been out there, but have probably been looked at more in isolation. One of them is the view of neuroscientist David Marr, who is very influential in computer vision, who proclaimed this direction of 2D to 3D reasoning, right? Really understanding the world from just 2D observations. And the second aspect, which has probably not been looked at that far, is the vision of neuroscientists Rodolfo Linas and Kenneth Craig. What they said is a creature must anticipate the outcome of a movement in order to navigate safely. And I argue that while we have done, at least in computer vision, a great deal of work to get us closer from 2D to 3D reasoning, what we have not looked at much yet is this second aspect of actually anticipating in order to achieve this safe navigation and interaction with our world. Now, in order to get there, I would argue that there is at least 4 steps that we are missing. And these are, on the one hand, reasoning between interactions of objects, revealing priors, particularly high-dimensional priors, more holistic understanding of objects as opposed to just labeling of pixels, and capturing ambiguity in these environments. Now, I don't have the time to look into all these aspects here in a 45-minute talk. We do have work on all of them, and I'm happy to talk about them offline. What I really want to focus mostly on now is holistic object understanding. Now, what do I mean by holistic object understanding? Well, in order to clarify this, let me first start with a very simple task of instance-level video object segmentation. It's that we're given or the task is to outline objects in a scene. Objects which we may not have ever seen before. So in this example that I'm showing you here, the classifier or the semantic segmentation algorithm has never ever seen fish before. The only thing it gets as observations is a first frame where the human tells the algorithm, these are the types of objects that I'm interested in. And then the algorithm is tasked to predict forward. Where do those objects, how do those objects deform, where do they go, and to track them going forward. Now, the way these tasks have been formulated in the probably late 2015s, 2016, was to actually take this first frame that the humans annotated and then train a classifier on this first frame data and run this classifier on the remaining frames. Now, that works reasonably well, but it has a big issue, right? The big issue is that you need to train a classifier on the first frame data, and if you think about running an algorithm like this on a phone, that's not going to work. It's way too time-consuming. You would drain the battery, and sending it offline into a data center has too big of a latency. By the time you get the classifier back, the scene that you wanted to segment is passed. So what we were really wondering about is, can we fix this issue? Can we change this process of training classifiers on first frame data into something that is able to run right away? And so the goal that we had in this first work was to develop an efficient algorithm that does not require this type of fine-tuning, and that kind of combines this detection and tracking ability, and that has an implicitly extraction of this temporal information. And since the work that we did, there have been a few follow-ups in this direction by Voigtländer and Wondrich and others. Now, essentially what we did is we changed the paradigm. As I said before, these classifiers were mostly trained to perform semantic segmentation on the first frame. And if you have to train a classifier on the first frame data, that's computationally expensive. So what we were wondering about is, instead of training a classifier, can we actually train to match? So can we train a matching-based procedure? And then matching during runtime is not something new anymore, right? If we learn how to match, then we just maybe need to fine-tune a little bit, if at all, and we can just run this matching then on during runtime as well. So, and that was essentially the high-level idea behind Video Match, which was with Yuan Ting and Jia Bin presented at ECCD 2018. So really the idea was to not train a classifier, but to actually train to match feature representations. So if I briefly walk you through this illustration here, is we are given two frames. The first frame is the image at time point 1, I1, and then we are also given an image at time point t, IT. And we're then applying your favorite neural net, whatever you wish, to extract some feature representation, x1 or xt. Now for the first frame, you're given both foreground and background data, and I refer to that as FG or VG. And I then split the features from the first frame into two parts: the foreground set, MF, and the background set, MB. And then I use this foreground set and background set and compare to these features in that set the features that I extracted from frame IT. Right? And then I'm literally just performing this matching now. It's no longer kind of a classification. All I need to figure out is, do those features match or do they not match? And I'm trying to train these CNNs to produce these features that allow us to perform this matching. Now we perform this matching in this soft matching layer, which I'm going to discuss in a bit. The outcome is then two similarity maps. One which tells you how likely does a feature map or how well does a feature match with the foreground set, and how well does a feature match with the background set. These are the red and blue rectangles. Then we perform some upsampling, concatenate them together, some softmax, and that gives you the output. Right? So now it's no longer classification based, it's really this matching based idea. Now, the one thing which I haven't explained yet is what happens inside these soft matching layers, and that is essentially illustrated here. Again, in one of those soft matching layers, we're given these template features. You're given the foreground or the background set, and then you're just computing a similarity function, right? Just standard cosine distance for all your features with all the elements that are either in the foreground or the background set. Then we are performing an average top k, which is nicely differentiable. We end up with a feature or a vector which is height by width cross 1. And after a reshape, you get this matching score, which was the similarity layers for either foreground or background that I showed on the previous slide. So all this is, very easy and intuitive operations that you can backpropagate through in order to learn your features. And some of those works that I mentioned earlier by Voigtländer and Wondrich, what they do then is, they make this matching layer parametric and extend these up into several hierarchies, which you can do in order to improve the performance. Now, there's a couple of extensions, right? If you look at an algorithm like this, there is two additional aspects that you presumably want to include. One of them is this online update, right? Your objects, they change over time, and you want to adjust to those changes. So what we do in order to incorporate this is we update the foreground and the background sets. If we are very certain about specific features, they get included into those sets. And the other aspect that you might want to include is some outlier removal, which essentially assumes that your object can't jump from, say, the left side of your frame to the right side of your frame within one step. So there is some certain temporal coherence that we want to take advantage of, and that is, very simply done usually by taking your prediction from the previous frame. You just extrude that, and only predictions that are within that extruded region are to be taken as positives for the next frame. And then if you get the initial prediction, you can see some outliers like this trash can here and something in the grass. And because it's not part of this extruded region, we will not take that into account going forward. Now, very simple, very easy idea. How well does all this work? So we compared this to a huge variety of competing algorithms on two datasets, the Davis 2016 dataset by folks at ETH, and then later on also Davis 17. And what we see in these plots is mean IOU on the y-axis, or contour accuracy, two metrics that people usually compare this to. And on the x-axis, you can see the time per frame. And we can see that our approaches, without updating or with updating, lie in this case in the top left corner. So they're reasonably fast and they perform quite accurately. Now note that the x-axis is logarithmic here. So that was very nice to see. And I should also mention that by now people have improved upon those techniques. So there is newer approaches out there that go way beyond the 80% that we achieved on both MIU and contour accuracy. Now, to give you kind of an ablation study on how well does outlier removal, background update, and foreground update do? You can see that for each of those steps you get tiny bumps in accuracy, kind of validating that if you add these elements to your algorithms, then you can improve the results further. Now, here's an interesting plot, which we were, at first very puzzled about. Again, showing you mean IOU on the y-axis and time in frames per second on the x-axis. There's a couple of competing approaches, and what you notice is those competing approaches, they have a very sharp increase when they perform the fine-tuning initially, right? So all these approaches they get the frame, they have to fine-tune, and the longer they fine-tune, the better their performance. Now, we got our initial result, right? Student was very happy, great, matching 80%. Now, let's also do this fine-tuning. Hopefully, we see an equal improvement. We are at 90% or, very good. And then we got this plot when fine-tuning our approach. And we're like, what is going on? Right? Why only this, mediocre improvement here? And until where we realized kind of the obvious, well, it's matching, right? And if it's matching and if it learns to properly match, if you give it new data, it doesn't have to adjust the matching procedure that much anymore. And even if you do try to adjust it, you don't get that much of an improvement anymore. So in the end, we were very happy about that result because it kind of confirmed that it's really not learning to detect anymore. It's trying to match, and because it's learning to match, the improvements are then smaller, which was kind of great to see. Although at the beginning we were kind of disappointed. Okay. Now here are a couple of visual results to see how well this works. You can see this. These are results on the Davis dataset, Davis 2016, and we get some decent performance on those results despite fast movements or appearance changes, occlusions. Sometimes you can see these effects of this extruding. But it performs reasonably well. You can also extend this, and I haven't talked much about this here, to multiple classes. Right? Instead of having 2 segmentation heads or 2 matching heads, you could have more than 2, which I skipped. But we did extend that, and you can see the results here, where we detect more than 2 objects. In this case, this is the same fish sequence, where we extract multiple instances. Okay, and some more. There's a large data set. This is essentially going through the entire data set, which I not force you to watch all of this. Looks fairly interesting. But, back to the point. Now, this is all great, and it works reasonably well. But what these items don't allow us, or don't do, is they don't understand objects as a whole. Right? They understand, there's a pixel here which I ought to be classifying as a human. But they don't understand what makes up for a human. Right? If I look at this audience here, I see a lot of people, I see barely any legs. But I know that you guys all have legs, at least I hope you do. And so items do not understand these aspects. Right? And what we really want to get to is, can we get items that understand objects as a whole? For instance, this slide here on the right-hand side, this image, where we know that the bedboard can't be floating in the air, right? It has to be somehow either attached to something or extended all the way to the bottom. Or, there's these elephants here, right? There's not just a bunch of pixels, they're elephants, and we know what makes up an elephant. Now, I would argue that humans are able to perform this task of what is referred to as amodal segmentation, not only segmenting what is visible, but also assigning or finding the objects as a whole. Now, it turns out that this is very challenging for AI systems. First of all, they have to reason about occlusions, and they have to understand what really makes up an object. How does an object look like as a whole? And they have to predict invisible parts, which is even challenging for humans to do. And probably one of the most challenging aspects is that it's really, really expensive to get reasonable ground truth data. Right? Imagine I would ask, at least if I asked my students, I'd tell them, here's a video or here's a set of images, annotate what you don't see. I'm not sure they'd be very happy about it. Now, nonetheless, there is some data sets out there, so some people apparently are happy about it. And there's 3 data sets out there. There's what is called the COCO-A data set, and there's D2S, and there's DICE. COCO-A is real data. It's a subset of the COCO data set, 5,000 images. There's D2S, which is real data, but mostly groceries on a table, which is probably not a day-to-day situation, even though sometimes we might run into that. And then there is DICE, which is synthetic data, but indoor and static. And the static part is the one that that we were really surprised about. Really all of them are actually image data sets. But the one thing that as humans we use a lot is temporal information. Right? Temporal information is the missing aspect in any of these data sets. Right? If I come back to these images that I showed you before, if you see those 2 kids running next to the car, and a second later they're gone, you still know that they are there somewhere. They must be hiding somewhere, right? They're not all of a sudden gone. So temporal information is a really, really important aspect. So how can we take this temporal information into account? And I think that is really something that was missing. So what we set out to do is to come then up with a data set for a modal instance level segmentation. Now, obviously, I didn't ask my students to go and just annotate videos, which would be even more challenging than annotating images. Instead, we turned to games that are out there, and specifically Grand Theft Auto 5. We had a summer of great fun. Now, we use that game because these games these days provide quite reasonable realistic renderings. Moreover, they have a really huge variety of different scenes, as you can see in the bottom there. Also, we can change the weather and lighting conditions as we actually please. And then it's reasonably easy to actually get ground truth annotations from the game, as I'll explain to you in a bit. So how do we get this annotation, right? Or actually, let me show you some videos, right? Here's what this looks like. And you can see that, some people are wearing shorts while it's snowing. Which I didn't imagine being possible until I actually came here to Canada. Or different lighting conditions. And you can see all the annotations that we are able to extract. So how do we get these annotations? So the nice thing that is essentially publicly available is a library which is called Scripthook 5. And it allows to really control the game, which was a great part of what we had to do. It allows to alter the weather conditions, the time of the day, the clothing. It allows and it permits to pause the game and to tag visibility of objects. Now, these three ingredients are really the important parts, right? Ensuring that there's a great deal of variety, pausing the game, and then being able to toggle visibility of objects. And now you might already, kind of see where this is going. So here's what we do. We start the game. We initialize randomly the weather, time of day, and clothing. Then we play for a bit, and then we pause. And after having paused, we first display all the objects, and we record the frame. Then we toggle the visibility of all the objects to false, and we record the frame. And then we display one object at a time, and we again record the frame. Now, this is great, gives us a huge amount of images that we can kind of compare to. But there's an issue, right? The issue is that comparing RGB pixels just isn't robust enough, right? There is shadows, there's reflections, and if you're looking, for instance, at the helicopter, right, if you're toggling the visibility to false, we wouldn't get a shadow of the helicopter because of the rendering. Yet, if you were to then just compare the frame where no object is visible to the frame where the helicopter is visible, we would segment it as these pixels down there as being part of the helicopter, which they're really not. So just using RGB is not good enough. Okay, so what else can we leverage? Well, it turns out we can actually place ourselves between the rendering engine of the game and the GPU. And that permits us to extract not only the RGB image, but also straight from the GPU a depth buffer and what is called a stencil buffer. A stencil buffer essentially giving you some form of class labels. Now, with that information at hand for all the objects displayed, as well as for only background, and for each of the individual objects, it's now not that hard anymore to just compare, say, depth buffers and stencil buffers as a sanity check to obtain the Amodal segmentation. So really what we do then is we look at the differences in depth buffer, we look at the differences in stencil buffer as a sanity check, and that gives us the Amodal segmentation that in the end we want to look at. Right? Something of that sort. And you can see objects like this dog that are, as a human, really hard to actually annotate. And obviously, it's also easy to get the visible mask, which is straightforward too, by just looking at the depth map. Now, that's great, but that doesn't get us all the way yet. Right? Imagine we do that for every frame, and then we still have to solve the assignment problem of which object goes where. The nice thing about this is that the game actually assigns a unique ID to every object, which we can also extract. So that enables us to obtain tracking information for both the visible mask and the invisible mask. The other one thing that I really want to emphasize is the level of detail that these semantic segmentation masks have. If you look at the hair here, we get really fine-grained semantic segmentations that even current image segmentation data sets do not have that level of detail. Now, another interesting aspect then is that the game also has object IDs or names for every object that it renders, and that allows us to obtain semantic class labels. In that data set, we collected 162 classes, and we made sure that 60% of those classes overlapped with the MS COCO data set, such that you have an ability to actually test this also on real-world data. So you train your model on this synthetic data, you can check on real-world data how well does it actually perform. Playing with these libraries, we found a few more interesting cues that we could actually get. Here's another fun one. Pose information for humans is in particular 2D and 3D pose information. 3D word coordinates and how it renders onto the screen is easily available. So we can get videos like this one where we have detailed key points in both 3D and 2D for humans, for instance. Despite all the occlusions, which is something that later on in this talk we're going to leverage. Now here's a few videos that show you again the diversity of this data set. And all the detailed annotations that you can use. Now, just to give you some statistics, again, I mentioned that there's a couple of existing data sets, COCO-A in the original version as well as a class-specific version, D2S and DICE, all of which are image data sets. This is the data set that I just talked about. This is the first video data set. And it has the number of object instances is at least one order or 20 times larger than any of the existing data sets, and that is largely possible because the entire annotation process is essentially automated. There's no human intervention anymore. All this is just take a computer or a few computers, have them play their game, and they do whatever they want to do, and they just dump the data onto some disk, and we later on just grab it. Now, obviously, then given this data, we wanted to know how far along can we go with this. We didn't, back then when we submitted this work, we didn't spend too much time on developing models for this specific task just yet. So we took an off-the-shelf mask RCNN. We slightly modified it to predict just the Amodal mask, which is really not what you should be doing. Because essentially it asks you to look at a table and predict that there's a human behind it, which doesn't make sense, but it's the first thing you probably want to have a baseline for. And then we also had mask joint, which what it does is it predicts modal segmentation and amodal segmentation at the same time. Again, I don't think this is exactly what you should be doing, but yet it's probably the first baseline that you want to have anyway. So we ran this, and here are then some of the results that you can see for those different approaches. Now, this table in isolation is probably not that meaningful. However, if you have the numbers for, say, COCO semantic segmentation in the MS COCO dataset in mind, you can see that AP at 50, which is in our case roughly for both modal and amodal at 40%. And for MS COCO, it's roughly at 50% right now, which says these data sets are roughly equally complex, which is great to see because we don't want to have a data set that is overly challenging and where you can't make any progress in the next 20 years. But we wanted to make sure that we have a data set which is somewhat balanced and is on par with what existing data sets allow or offer. And then we have other metrics for heavily occluded, lightly occluded, medium and small objects, and kind of breaking it down. And you can see that small objects are still particularly challenging, which is also true if you look at classification, or if you look at results of mass RCNN on, say, the standard COCO dataset. Some more quantitative results where we show, does this dataset actually provide any benefits? So what I'm showing you here is the fraction of Davis data, the one that we used early on for semantic video segmentation. And then if you take the video match model that I presented earlier, and you just train it on COCO, and then you run it on Davis, that will be 0%, and then you fine-tune it on 10% Davis data, 20, 30, 50, and 100% Davis data, and that's kind of the number that I showed you earlier. Now, if instead of fine-tuning on COCO, you fine-tune on this dataset that I presented earlier, the Sailwaz dataset is what we call it, you can see a decent bump in performance. So you can see that despite the fact that it's actually synthetic data, it allows you to get some performance improvements by leveraging these temporal aspects, which was great to see. Okay, some more qualitative results. You can see that it does a decent job, but it's still not quite there yet. It's still missing a lot of legs, so there's a lot of room for improvement here. And that is really part of the message here is I think this is a really important task that we should be looking at as a community going forward. But these models still have a lot of shortcomings, as you can see here. They're cutting off, for instance, even the ground truth is cut off, and it segments more the pizza than the human. And here in this video, you can also see it starts to hallucinate that there are people behind it, but those are not proper people shape, which is obvious given the fact that we're just running a simple mask RCNN head. There's much more interesting approaches going forward that you should be using in order to properly incorporate priors, like what a human actually looks like, right? And I did mention earlier that these are directions that we are looking into, and I'd encourage all of you to look at similar questions as well. All right, so to wrap up this part of the talk, what I talked about was a dataset for semantic A-model instance-level video object segmentation. It has ground truth annotations, including models, segmentations, A-model segmentations, semantic class labels, and human pose information, which is all publicly available. You can find it at the link down there. And it also permits to transfer to real world the COCO A dataset. The COCO A dataset doesn't have temporal information available. So if you develop models that leverage temporal information, the transfer is not that easy to assess. But if you are developing models on an image basis, then transfer is reasonably easy. Now, I motivated this talk with anticipating, and this is the aspect which I kind of wanted to look into in the remaining 10 minutes, 50 minutes.
Yeah.
Okay. Which is kind of simplifying the problem a little bit, and instead of looking at forecasting, for instance, semantic segmentations, let's take a step back. Let's try to forecast human pose information. Specifically, I wanted to look at pose regression tasks in general. And pose regression tasks, one of them is 2D to 3D pose estimation. So you're given the 2D coordinates, and you want to regress to 3D world coordinates. Another pose regression task that you might be familiar with is pose forecasting. Right? So you're given a starting sequence of joints, and then you want to predict forward how is that sequence going to evolve. And the third task is a skeleton-based action recognition. You're just given the skeleton, and you want to recognize what type of action has been performed. Now, how have people typically formulated these types of tasks? Well, the standard approach, very common to this day, is concatenation of your joint coordinates. So you literally just take your coordinates, x, y positions, stack them together, feed them through a deep neural net, and then you either regress to 3D points, 2D pose futures, or skeleton-based action recognition. Now, if you think about this, right, one thing that is really missing is the structure within your data, right? And we have heard great talks about graph neural nets leveraging some type of structure. And what we were wondering about here too is, can we take this structure of human poses into account more explicitly? Now, what structure am I referring to? Well, the structure that I'm really referring to here is this left-right symmetry, which, you know, this baby here is really exploring, you know, trying to see what's happening there. Essentially, you're trying to figure out that, you know, for every pose, if you look into the mirror, there is a similar pose that might give rise to either the same action or you know, an equivalent forecast. So really the expectation that we have of models is take a pose, feed it into a model, for instance, for forecasting. Now take a mirrored pose and feed that into that exact same model. Then you would expect that the output should be, you know, transformed in an equivalent way. Should also be a mirrored pose. Problem is that many of these models that are developed these days do not provide these guarantees. And, you know, we were wondering, does that have to be the case? And in fact, how can we have these models provide these guarantees? If they would provide these guarantees, they should be much easier to train, or they should need much less data to train them. That was our hope. Now, the way people usually enforce this is via data augmentation, right? Just like you would for training images, where you do left-right flip, you can do a similar thing for poses. Slightly more complex, because what you need to do is you first need to do step one, which is just left-right flip, but then you also need to swap the labels of your joints, otherwise you're not getting a proper human pose, right? Human pose is kind of chiral, meaning it's not exactly superimposable. So you need to pay attention to that last step that you cannot ignore. Now, what is our disadvantages of data augmentation? Well, first of all, you need to learn this chiral equivariance from data, which is something that is sample inefficient, and also it's computationally more demanding to do. So really the question was, can we directly incorporate this structure into deep nets? Can we develop deep nets that are equivariant with respect to this pose transformation? Okay, so here's the picture of, you know, chirality nets, which is an answer to that question, which is yes, we can do that. And what I'm going to tell you about is then how exactly we achieve that. So again, the goal is you have an input pose. You can transform it with respect to the corresponding chirality transformation. You put either of those poses into your model, and the output that should then also adhere to the corresponding chirality transformation. Okay, how do we achieve that? Well, in order to tell you, let me first introduce a little bit of notation. So what I'm going to do is I take this vector x, which represents my pose, and this vector x lives in a space of j r in, jl in, jc in multiplied by d in. So what is that? Well, j r in essentially all the coordinates of your left part of the pose. Then the right part of the pose, sorry. L denotes the left part of the pose, and C denotes the center part of the pose. Right? And then D in is essentially the dimensions that you have per joint at your input. So for instance, if you're talking about 2D, then it's 2D coordinates, U and V. Now, we'll also split these vectors, left and right vectors, into whether a coordinate ought to be reflected, meaning multiplied with -1, or whether it shouldn't be reflected when you apply the chirality transformation. And that's the dark parts, and the light parts are the ones that are not reflected. Then we just stack all those coordinates at the corresponding positions, sort them. That's our vector x. So it's literally just an encoding of your pose in a specific order. Now, why do we use this order? Well, the reason we use that order is because then this chirality transformation, meaning reflection, step 1, and the chirality transform, the swapping of the labels, is very easily done with just 2 matrix multiplies. Step 1 is just negating dimensions for the corresponding joints, which is a multiplication with a diagonal matrix with entries -1 or +1, depending on which entry you're going to hit. And step 2 is just multiplication with a permutation matrix that just swaps these 2 vectors. Got it? Very easy. Okay, now let's try to develop a very simple deep net layer that respects this chirality transformation. And specifically, I want to look at the simplest deep net layer that you can look at, which is just the bias layer. So the only trainable parameters is the bias. So it's the B's. So you have your input data X, you add some bias to it, and you get your output. Now, which structure do you have to enforce in this bias layer so as to make it chirality equivariant? Okay, so here's our data, X again. Here's our bias layer. And here is then X plus B, which is Y. Now, note that the B has a very specific structure, meaning the colors, or identical colors, denote identical values. So this subvector here has the same values as this subvector down there. Now, if I enforce this structure, if I enforce these parameters to be shared, then this is equivariant with respect to the second step. Now, the second step was this swap of transformations, right? Just this swap of my input data X. Now I swap my input data X, I add B to it. Now, if I enforce these pink boxes to have identical values, right? If I swap the same thing at the output, then the result is again identical. So by enforcing parameter sharing, I ensure that my deep net, or this bias layer, was equivariant with respect to the second step of this chirality transformation. Now, what I haven't looked at yet is the first step. Right? That part we also need to take into account, and that is slightly more tricky. What we need to do is we also need to have this first block being the negative of this first block, and that's illustrated by this darker color. Now again, same illustration, full chirality transform. So first part is we take our data X and we just multiply some parts with -1. That's the reflection part. And then we swap the input. And now we do the same thing on the right-hand side. And I'll hit again the first parts with -1. This changes this way. And then I perform the transformation. And surprise, identical. Right? So that was a bias layer. In that way, we designed a bias layer that respects this chirality transformation. Now, this is essentially what I just talked about. This part over here, right? This is your bias vector, 0 here, whatever variables you can drain here. This part is the negative of this first part, and the second part is shared and identical. Now, you can go through the same steps for the remaining parameters of a fully connected layer, and the structure looks like the one that you see here, so it's slightly more complicated, but you can see parameter sharing patterns here, and even in all symmetries that we enforce. But it works out. If it works out for fully connected layers, you can also make it work for convolutional layers, you can make it work for LSTMs, GRUs, batch norms, and so on and so forth. We spent a great deal of time, looking at all this and working all this out. And you can find actually all this online. I'll give you the link in a bit. Now, kind of to wrap up, how well does all this work? We took the task of predicting 3D pose given 2D pose. We also have forecasting and classification in the paper, which I'm not going to talk about here in the interest of time. The metric is the standard metric that people use, mean per joint position error between prediction and ground truth. And we took the state-of-the-art model by Pablo and others, and all we did is just replace their layers with our chiral equivariant version. That's it. Okay, so here are some results. You can see different amounts of training data that we used, error metric on the y-axis. You can see in most of the setups, few training data over here, more training data over there. In many of these setups, just by replacing the layers, by enforcing the structure explicitly, we can outperform them. A ton of numbers, most of which are not important here. Again, what I want to point your attention to is the baseline model by Pablo and others, which uses test data augmentation, meaning they actually run their model twice during inference on the original pose and the reflected pose, and then they average the result, which gives them 46.8, whereas we just run the model once forward pass. Because of parameter sharing, it's even more efficient to run. We can slightly outperform them. And you can compare if you would not use test data augmentation, they get 51.8, whereas we get 46.7. So there is a lot of improvement that we can squeeze out from this perspective. On another data set, that's the human EVA data set, we also ran the results, and you can also see improvements here of our approach compared to competing methods. Some more qualitative results. Forecasting, which I'm going to skip. Just showing you the video, and this is kind of the burn-in period, and then you can see how the models evolve over time. And you can see that existing approaches have some struggle keeping the structure. Now, with that, let me. I should obviously show this slide here, kind of summarizing this part. So what I talked to you about is these. In the second part is chirality nets, which provide equivariance guarantees. Because of those equivariance guarantees, they are very efficient to train. They have a reduction in computation time because you're sharing parameters, so you don't have to perform certain operations twice. And they're specifically suitable for human pose regression, and you can find paper and code on the website that I'm giving you there. Now, with that being said, let me find my concluding slide. Which is right here. So I guess going forward, the main message that I really want to bring across is that oftentimes, these days, it still seems reasonably easy to make progress by just applying a deep net onto some data and then trying to beat the numbers or beat the benchmarks. But what I really want to bring across is to think a little bit about the problem that you have, the structure in your data. And oftentimes that actually helps you, leveraging the structure helps you really gain out of and get even more out of your data. Now, kind of going forward, what we are interested in now is to apply and use some of these techniques for this Amodal forecasting. I did not get much time to talk about our work on GANs that we also want to leverage in this context, but seems kind of intuitive. Happy to talk about this more, and I really hope that this brings us towards algorithms and models that really learn what it means to anticipate in the real world, kind of combining these two visions that I alluded to earlier, 2D to 3D reasoning and anticipating in order to navigate safely. With that being said, I thank obviously my funding sources. I thank you for your attention. Feel free to reach out either via questions now or via email or on my website. Thank you.
We got time for a couple of questions, quick questions. Yeah.
So I was wondering, say suppose this A model that you have built, right? Isn't it just my question? I'm just thinking about it. Can't we use a thermal infrared camera or something like that, because it will be more, it will be better, it will be more accurate, and the more the adaptation, the lesser the price will be. It is ranging from like $100 to $200. So if more cars or more robots put it in their system, it will become cheaper, right? So isn't that a better one? And also higher frame rate, can capture even higher frame rate. So why not in that direction?
Right, that's a great question that you're bringing up here. Is I guess two questions. One is, this is synthetic data. How applicable is that to real world data? I guess the answer here is because we also record depth data. So you can actually train models on depth data, which you can already get from sensors and then apply it to there. Now, I am not an expert in infrared by any means, so I don't exactly know what infrared would provide us. So that might be a great opportunity going forward as well, which, yeah, as I said, I do images. I would not know what advantages you get from, say, infrared data, which I would be very happy to chat about if you happen to know something.
I had one more question. The chiral nets that you were talking about, right? Say, suppose, did you run the model twice? The reason is you have to run once because then you will get one pose, and then only you will be able to feedback this pose into the chiral. I hope I'm pronouncing it right.
Chirality.
Yeah. You'll be able to get the mirror image. So did you?
So in our model, in our approach, we do not need to run the model twice, right? Because our network guarantees that either the original pose or the reflected pose, it will give you the corresponding equivariant output. So in our model, when using these layers, you don't have to run your model twice. In contrast, competing approaches like Pablo and others, they do have to run their model twice, or they usually run their model twice and then average the results. So the way they obtain a chiral equivariance is by essentially taking the input, flipping the input, running both through their model, and then averaging the result, which is another way, but obviously it's twice as expensive as what we did, or more than twice as expensive. Last question.
So that was a great talk. I really enjoyed it. So going back to the segmentation model that you proposed, I guess the major assumption there is like the temporal information. So essentially, you have the maximum mutual information between a number of frames with your reference, right? So one question is that do you update the reference frame, or you just keep it fixed and everything is being compared to the reference frame?
So I guess. First, the video match results. The reference frame is really what is given to you. So a lot of features that we extract are coming from the reference frame. Now that being said, I did mention that we are adding new features to this set of foreground and background features if they are if we very confidently predict that they are either foreground or background. Sure. So we have this additional augmentation step, and it helps you improve the results slightly. I don't know whether I can very quickly jump to this. Let me see, where was this slide? I guess it was this slide here, right? This is if you update the background and if you update the foreground set. Right, you can see if you don't do it, then you get 79.6 with updating background and foreground. You get slightly improved.
Right. But the main question is like if you have like a sequence of the frame, then essentially your similarity metric should be somehow invariant to all of these changes, right? So it should potentially maximize the mutual information between the two, right? Between the reference and your query, right? I don't know whether the cosine would actually be that invariant. So I was wondering like what other similarity metrics you.
Oh, I see. Okay, now I see where you're going. Yes, there's different similarity metrics that you can investigate, and other people that followed up on this work have looked at some of these similarity metrics. I am not aware that anyone looked at mutual information, which would be a very natural metric to actually take into account. And yeah, great question. We have not looked into that specifically, so I couldn't give you a number.
Okay. I guess we'll thank Alex once again.